All right, so we are in chapter 3.6, chapter 3, section 6 of calculus. So we're still thinking about interesting ways to use the derivative. That's what this whole chapter is about. And here we're using it to think more about graphs and analyze graphs more. So these are going to be long, tedious problems just because we're going to really be analyzing like every part of this graph. So we're really just going to go down the list. So first off, they want us to find this first derivative. Well, before I do that, I'm actually going to copy this list down to the next problem. So we have it fresh and blank down there. And so let's do it. So first derivative. Well, to find the first derivative, we're going to have to do the power rule. So let me write a little smaller here. F prime of x is going to be our quotient rule we're going to have to use. So the derivative of the top, so I'll write that as 2 times 2x times the original bottom times x squared minus 4 minus the original top times the derivative of the bottom, which is just 2x. And all of that over x squared minus 4 squared. That is a crazy first derivative. Especially to have to do it twice. So I guess I need to combine like terms on the top. So 4x cubed minus 16x. Same over here. So this is a minus 4x. So that's going to be, that is kind of nice then. That's minus 4x cubed. And then 4 times 9 is 36. It's plus 36x over all of that. So the all of that's not going to end up going anywhere. But everything on the top, look, that the other ones combined. So it's 20x over x squared minus 4 squared. That is the first derivative. Now the second derivative, we got to take the derivative of that. So let's see. F double prime of x is, we got to use just quotient rule again, I guess. So the derivative of the top is 20 times the original bottom, which is now to the 4th, and then minus the derivative of the bottom, which now we're going to have to use chain rule. So see, that's the power rule. 2 to the front, power decreases by 1. Multiply by the derivative of the inside, times 2x. And then multiply by the original top, times 20x. And now it's going to be divided by all of that to the 4th. Right, which I already did up here, but I was definitely not supposed to do that up there. That was just squared, because that was just supposed to be the original bottom, the derivative of the top times the original bottom. Okay, now we're correct. That's just squared. So that's the derivative. They really need me to multiply all of that out. I guess this happens, because this is nice how it happens sometimes. There's an x squared minus 4 and both of these on top, so those get canceled out. So now I don't have to FOIL. So this isn't that bad then. 20x squared minus 80. And let's see, that's 40x squared. Wait, we have 2 times 2 times 20. That's 80. And then the x times x, and then the minus. So yeah, minus 80 x squared over x squared minus 4 to the 3rd. So then you combine like terms. Negative 60x squared minus 80 over x squared minus 4 to the 3rd. Okay, that's our second derivative. I guess there's no reason to doubt it. We did everything right. All right, so now we've got our x-intercepts. Let's change colors for our x-intercepts. So x-intercepts. What is the x-intercept? It's when the y value equals 0. So we're going to set this entire thing equal to 0. And the whole idea with fractions is if we multiply just by the bottom of the fraction, it goes away. So when you set a whole fraction equal to 0, you just need the top to equal 0. And that's pretty easy to see. You divide by 2, add 9, square root both sides. Your x-intercepts are at plus or minus 3, comma 0, of course. And then your y-intercept is where you make x equal to 0. We'll just look at that. You make that 0, you make that 0. 2 times negative 9 over negative 4. So let's see, the negatives cancel, the 2 cancels, so it's just 9 over 2, 4.5. Okay. Vertical asymptotes. So the vertical asymptotes are where the function is undefined. So that's going to be where the bottom is equal to 0, where x squared minus 4 is equal to 0. Because, of course, you can't divide by 0. So that's easy enough to see, plus or minus 2. Horizontal asymptotes, that's your in behavior. So that's what you're thinking about when you make x equal to positive infinity or negative infinity. And look at how here, the powers on the x are the same. So then they're just going to cancel, and you're just going to be left with 2. So your horizontal asymptote is at 2. Now let's see. Someone thinks my second derivative is wrong. Let's look at that once we use it. Because for our critical number, we just need the first derivative. So we're going to take our first derivative and do 2 things with it, right? We got to set it equal to 0, and we got to set it equal to undefined. So first off, when it equals 0, and remember, this is kind of a beautiful part about the fraction too, because when you set a fraction equal to 0, it's when the top is equal to 0. So that's x equals 0. And then when you set it to undefined, that's when the bottom equals 0, when x squared minus 4 equals 0. And that's plus or minus 2. So even though the function is undefined there, we're still going to count those as the critical numbers because it might change, it might change from increasing to decreasing there. We should still look at that. And then now we need the possible points of inflection. So that's when we set the second derivative equal to 0. And so let's see about our second derivative. I think your second derivative is wrong. Isn't that supposed to be an 80 and not a 60? You're talking about this right here? It looks like I wrote an 80. It looks like that's supposed to be an 80. Can write it better. Yeah. I think that's right. I thought you said 60 was not looking. I might have said 60. I might have read it wrong when I read it. Said it wrong when I read it. Alright, so that means this is at least the correct second derivative. So we want to set that second derivative equal to 0. I guess we want to do undefined as well, right? We should still be thinking about what happens when it's undefined. Because, of course, this is a rational function. So it's going to have asymptotes there right from the beginning. But that's still going to... So it's not going to be a point of inflection. But it still might change concavity there. Which they don't ask for. But I feel like is part of what we need to do here in order to sketch the graph. So let's see. What are possible points of inflection? Set the second derivative equal to 0. So that's negative 60x squared minus 80 is equal to 0. Because, of course, we just need the top to be 0. So let's see what happens then. Subtract the 80, divide by 60. That's 8 over negative 6. That's negative 4/3. Square root both sides. So x is plus or minus 2 over root 3. Okay. And then, of course, when the bottom is 0 to make it undefined. So plus or minus 2. All right. I don't know if I can do this for every single graph. It's already been 20 minutes and we're still in the first one. So what's the domain? The domain is just anything except for this. So the domain, when that equals 0. So the domain is just that x cannot be plus or minus 2. We don't need to write that in interval notation. Symmetry? Well, actually, I guess, yeah, now that we look at it, it should have some symmetry, right? Because of this x squared. If you think back to like even and odd functions, if we found f of negative x, the negative would just cancel out, and that would be equal to f of x. So it has y-axis symmetry. So I guess then they want us to test the intervals to see increasing or decreasing. So let's see. Maybe we start sketching the graph now. We can sketch pretty much all of the graph. You just think back to pre-calculus, what we did then. So x-intercepts of 3 and negative 3. So there and there. Asymptotes at 2 and negative 2. Let's go ahead and try to make it look good. 2 and negative 2. And y-intercept of 4.5. So that's right there. So yeah, I can definitely already see kind of the vibe of what's happening. Is that we've got this little parabolic thing here with the asymptotes. So of course not a parabola, but with the asymptotes. And then just back to pre-calc, we can see how we have these single root asymptotes. And since they're single root asymptotes, they have to be coming from the other side. And so we have something like that. And we never did say we have our horizontal asymptote at 2. So let's put that on like this. And so there we go. I mean, this is just our classic rational function. You've got your asymptotes. They create your different sections of the graph. And then you know you have to have stuff in every section. And let's see. What did we find in terms of points of inflection? So our critical numbers, 0 and plus or minus 2. So here we have our 0. We have our minimum, our relative minimum there at x equals 0. That was one of our critical numbers. And then the other critical numbers were just the asymptotes. And so it is interesting to see, like, if it goes from increasing to decreasing, but you actually see it stays increasing. Like, it does have that gap. So if you're listing where it increases, then you should include that. You should put a break there. But it's increasing, stays increasing. Now, what about the points of inflection? Maybe we missed something that we haven't seen yet in here. And it might change concavity somewhere at 2 over root 3. What's 2 over root 3? It's like 1. A little bigger than 1. Because root 3 is going to be like 1.5, 1.6. But more than 1. So in between 1 and 2. So somewhere in here, there's a possible point of inflection. That's not going to be true. That's not going to have a point of inflection there. Let's see. Because if I think about the number line thing, and I think about here we have 2 over root 3. And so I'd have to plug in something. I guess I could plug in 0. Because it just has its possible changes at, and then like 2. But I have to plug in something between 2 over root 3 and 2. I guess I could probably just think about it. So, and I'm trying to think about the concavity. I'm trying to find what sign the concavity is in these places. So if I plug in x equals 0 to the second derivative, that'll tell me about the concavity. So if I plug in 0, I get negative minus negative, so a negative on top, and a negative on bottom. So it should have a positive concaving up concavity in this section, which we see makes sense. But then is there ever concaving down here? So if I plug in something that's just less than 2, what's going to happen? Well, it's like I can plug in 2 on the top. That's fair, and that's just like a negative. So I get a negative on the top. If I plug in something just less than 2 on the bottom, that's also going to be negative because it's going to be like 3.9 minus 4, which is a negative. A negative cubed is negative. So that's a negative over a negative. That's going to be a positive. So it's also positive in this place. Is this the hard way to do it? This is the way that I know to do it. So that shows that it's going to be concaving up in both of those places. That's true. I could more just think about the graphs of the derivatives. So this is definitely what our graph is looking like. Let's go to Desmos. I can check the second derivative there too. I'm surprised that we got that 2 over root 3. So what do we have then? The original function was, so f of x equals 2 times x squared minus 9 divided by x squared minus 4. So there's our graph for sure. There's definitely no changes in concavity, which I definitely didn't think there was. But that's why I'm curious. So now, can I do f double prime of x? F. I'll just type in f of x first. So then I can just kind of see if I add the apostrophe, then add it again. Nice. So that's the derivative. Is that like what we got? No, that's not what we got. Oh, yeah, it is. Yeah, it is. Maybe. But there should be x-intercepts. Let's see. Is that what we got? What's negative 60 x squared minus 80 divided by x squared minus 4? Cubed. Okay, yeah, no, we did get it right. Good. Good. Oh, and there's no x-intercepts because of the negatives. That makes sense. Okay. So yeah, we did everything right. So we still got that possible point of inflection. So interesting. Notice how we had the what I was going to say. I totally lost it. I totally lost what I was about to say. But yeah, this is right. So really, like, looking at the derivatives didn't really help us there. But it is interesting to see that we found that possible point of inflection, but it ended up not being a point of inflection, which we could see from the graph. But I felt like we should look at more from the derivatives too, because there could be like some wonky stuff. Like one of the things we'll see, but when looking at the derivatives, is when it has that little hump when it crosses the horizontal asymptote on the outside, but then goes back under. That's one of the things we'll see here. Wow, we spent a long time on that. And that's just one. And they want us to do that for all of these. My goodness. But yeah, let's do it. Maybe these will be quicker and easier somehow. So I'm actually going to rewrite this function right away because it is going to help us take the derivative. And I can just see it, so I'm going to do it. Because we just did this on a problem. I guess we just did this on the integral of the day. If we hard it like this, you see what we have here is x times x minus 2 over x minus 2 plus 4 over x minus 2. And so that just means this function can be rewritten as x plus 4 over x minus 2. And that changes nothing about the function. And one thing that shows us is our slant asymptote. So I'm going to go ahead and put it with the horizontal asymptote because we're not going to have a horizontal asymptote. That's going to be our slant asymptote, y equals x. And then while we're down there, vertical asymptote. So we still have this fraction, and it's going to be the same as we can see from here. Just when the bottom of the fraction equals 0, that's x equals 2. Then let's see, x-intercept, we set the entire thing equal to 0. So that's easier with the first. We've got to say when is this thing, the top of it, equal to 0. Now that's super annoying because you can't factor it. So you've got to just use the quadratic formula. Or complete the square. And you know what? I'm going to complete the square because completing the square actually is a really nice way to do things. Although I'm not sure we're going to get real solutions anyway. Yeah, because see, this is what happens when we complete the square. And so when we add this over here, x minus 1 squared equals negative 3. And we're going to get no solution, no real solution. So there's no x-intercepts. Y-intercept when x equals 0. Well, when you plug in x equals 0, these go away. Maybe that's actually easier to see on the other one, but it's both easy. You get negative 2. So we have a y-intercept of negative 2. Okay. Now let's find the first derivative. So when we find the first derivative, I definitely want to look at this way of writing it. Because now we can just find the derivative of x, which is 1. The derivative of the second part, which I actually think the best way to think about that is quotient rule. So quotient rule is the first part's just 0. You end up with just minus 4 times x minus 2. Or no, just 4 over x minus 2 squared. I mean, chain rule is easy enough to think about that too. But that's what it's going to be. That's your first derivative. So then your second derivative, you've just got to take the derivative of 1 is the 0. And then the second derivative of, so then the second part, you say the derivative of the second part. And that's just like a power rule or a quotient rule thing again. I'll try to think about power rule here. So you rewrite it as minus 4 x minus 2 to the negative 2. So then you power rule, it becomes 8, positive 8 now, over x minus 2 cubed when you put that back down. All right, so let's see. Looks like now we're ready to solve some stuff. So critical number, when the first derivative is equal to 0. So I'll say when 1 minus 4 over x minus 2 squared equals 0. So it would barely be best to combine that into one fraction first. So that's x minus 2 squared minus 4 equals 0. Because then we just ignore the bottom, because then we have a fraction. And then I would just expand that. So x squared minus 4x, because then we have plus 4 minus 4 equals 0. Those go away, and you see that it's x equals 0 and 4. Those are the critical numbers, 0 and 4. And then possible point, oh wait, also undefined. This is going to be the same idea with the asymptote, right? But we'll still do it. When is this undefined? When x equals 2. So I guess we technically have a critical number at x equals 2. Also notice critical number, not critical points. But the same thing. So possible points of inflection is when the second derivative is equal to 0. Second derivative is never equal to 0, because look at how the fraction's just 8 on the top. When's the second derivative undefined? Again, when x equals 2. But that won't be much. Domain, just the original function when the bottom is equal to 0. X can't equal 2. Symmetry, there's no symmetry here, because notice how we have the x squared and the x. That's going to mess up any type of symmetry that we're going to have. And then I guess technically now we need to test the intervals. So let's see. Let's go ahead and sketch our graph. This is the order we did things in last time. So we're going to sketch our graph. It should be nice looking enough. We need to have straight lines here. So straight lines, straight lines. What do we got? We got no x-intercepts. We got this. We got our asymptotes. So we had our slant asymptote at y equals x. So that's like there. We had no x-intercepts. We had vertical asymptotes at 2, at 1. One of them at x equals 2. And that's about it, right? And so, I mean, again, this is kind of just your classic rational function thing. It's like, you know it has to go through this point. But I guess here's the question is you don't know. It's like, does it turn around and do something like that where its maximum is here? Or does it turn around and do something like that where its maximum is here? And that's what the first derivative and our critical points are going to be able to tell us. Or, yeah, it could just turn around right in the middle, which actually looks like maybe what it does, because that's our critical number at x equals 2. Okay, so that's where it's going to end up turning around. We can confirm that when we actually test the intervals, but if that's where we have a critical number, that's where it's going to end up turning around. And then we know we have to have something like up here, because again, like single root asymptote, algebra 2 ideas. So that's probably going to be the critical point of 4. Something like here, so it's going to end up looking like this. Yeah, I like that as our graph. Let's see what this question is. Can you have a possible point of inflection where the function doesn't exist? I thought that the function had to be continuous through the interval for a point of inflection to exist. Well, it's definitely not going to be a point of inflection. I mean, definitely not, because it doesn't exist, so it's not going to have a point there. So maybe I shouldn't be listing that as a possible point of inflection, but I'm more thinking about that, and you could say the same with like critical points or critical numbers, that you're definitely not going to have a critical point at x equals 2 because it's an asymptote. But I'm also thinking about those in terms of like changes in increasing, decreasing, or changes in concavity. So like, no, you definitely can't have a point of inflection at x equals 2 because there's no points there, but it does change concavity there. And so if you were lining up one of those number lines to check concavity, you would want to check on either side of 2 because the concavity is going to be different on either side of 2. So why list it as a possible point of inflection? Because I just want to go back and remember, like, those are the points you're going to have to check. So, like, it has, like, I guess a point of inflection needs 2 properties. One, that it has to change from increasing to decreasing there, and 2, that it also has to exist. And those have the first property of points of inflection, that it is changing from increasing to decreasing there, but not, it just doesn't actually exist. So, no, it won't be a point of inflection. I think the main thing with these is, like, they're just asking us to analyze the graph. So I'm just thinking about the important stuff we'd have to think about when we analyze the graph. They're not exactly directly asking us these questions. But that's a good question. I mean, would the AP do that? Would the AP say, like, what are some possible points of inflections and not want you to list 2? I guess maybe they wouldn't. Well, it can't be a point of inflection, but it will change concavity there, potentially. And so that's why I'm thinking, so what are possible points that it changes concavity? I guess that's really what I list. I didn't list possible points of inflection. I listed possible points that it changes concavity. Now for critical values, you do set it equal to 0. But it's not going to be a critical point because it's going to be undefined. So I feel like that same thing should apply to the possible points of inflection. But maybe that's the difference. That's maybe why they say critical number here versus critical point. I don't know. I'm not too worried about that. I would list it because it could change concavity there. Like if we were going to list out, if they then asked us what are the intervals that it's concaving up and concaving down, that 2 would matter. Like if we were going to do that looking at the number line, that 2 would matter. I suppose we can glance in the textbook, see what the textbook did. Oh, maybe not. I'm going to pause the recording for a second. So we figured out in the textbook that technically to be a critical number, it does have to be defined. And the same for points of inflection. So technically I shouldn't have listed that 2 up there or that 2. So now I just want to make sure that indeed this is still, these are where it turns around. So I think the best, most conclusive way to do that is to be thinking about like the number line stuff. I guess we should look at 2 here maybe as well. So let's plug in, if we plug in, and what are we plugging into? We're thinking about increasing, decreasing right now, where the function is increasing and decreasing. So that means we need to plug into the first derivative, which is up here, this 1 minus 4 over all of that. So if I plug in on the left of 0, plug in a negative 1, I get 1 minus, oh, that's kind of annoying. Well, yeah, that's fine. So if I plug in a negative 1, I get 4 over 9. 1 minus 4 over 9 is positive. So in this section, it needs to be increasing. So that works with what we said. And then what if we plug in a positive 1? If we plug in a positive 1, we get 4 over 1, which is just 4, and then 1 minus 4 is decreasing. So that is there. So that goes from increasing to decreasing. Awesome. So now if we plug in like 3, we expect 3 to also be decreasing. Which is true because 3 minus 2 is 1, 4 over 1 is 4, 1 minus 4 is decreasing. So that's decreasing. But then after 4, plug in 5, just like before, you get 5 minus 2, which is 3, 4 over 3 squared, 4 over 9, 1 minus 4 ninths is a positive number. So then it is increasing after that. So yeah, very confident with what we said. And yeah, if you see those comments over there, that's why the second derivative test is kind of scary to use sometimes. So if I'm trying to be super definitive about it here, like it already made sense. Like I think our logic sticks about what we said. This must be turnaround at 0 and 4. Just because we did find those as the possible turnaround points, and we know it has to turn around somewhere. And I feel like we can just always conclusively get it by doing this, by looking at those intervals of how it's increasing and decreasing. Very nice. Lastly, for this problem, let's look at the graph. I don't need to confirm my derivatives. X squared, well, x squared minus 2x plus 4 divided by x minus 2. And is that exactly what we did? It is. In a way, at least. Doesn't look like it is, but that's what we did. That's what we did. We got all the key parts of it. It's easier. Yeah, it's easy. It looks more like what we did when you stretch it out like that. Yeah. All right, very nice, very nice. I guess I could have counted that out. I actually plugged in. That's what we should have done. We should have found this actual minimum because we did do that wrong in our graph. Because we should have been able to, we can say, and we should have calculated, that we know it turns around when x equals 4. So we should have said, what is f of 4? Actually plug that into the function. 16 minus 8 plus 4 over 2, which is 8 minus 4 plus 2, which is 6. So that should have showed us that we do know for sure that this point is right here. Which isn't a big deal. But we should have done that. But yeah, there we go. That's our graph. Man, this is going to be one of the longest videos I'm going to have. This is a lot of problems. Alright, so now we're doing the same exact thing with this function. So let's see. Let's not find the derivatives yet. So honestly, we don't even necessarily need to. Let's just do that if we need to. So what are the x-intercepts? Set the whole thing equal to 0. So when the top is equal to 0, so that's when x equals 0. Which makes the y-intercept nice, because we make x equal to 0, it's just the same thing. So let's go ahead and start sketching the graph now. When did I start drawing thick again? So we've got 0, 0. And then we've got vertical asymptotes. Interesting, when the bottom is undefined. So the square root of 0 is 0. So we're really just looking for where x squared plus 2 is equal to 0. And that's that x cannot be plus or minus root 2. So that will be the domain. That will also be the asymptotes. So when we sketch that, root 2, that's like, I think that's 1.4. So I'll just do it right about in the middle here. Boom. Okay, that's good enough for that. Horizontal asymptotes, when x is infinity, so that's like what we did last time. When you plug in infinity, you get infinity over the square root of infinity squared, which is just 0, because it's infinity, or no, it's just 1. Ah, but this has the different sides, doesn't it? This has 2 horizontal asymptotes. Because when you plug in positive infinity, you get infinity over infinity, square root of infinity squared. So that just cancels out to be positive 1. But when we plug in negative infinity, this ends up being negative infinity over infinity. So that's negative 1. So this is going to have two horizontal asymptotes. Plus or minus 1. So as we go to the right, it's going to be the positive 1. As we go to the left, it's going to be the negative 1. Interesting. So that'll happen with square roots graphs sometimes. I think we saw that last section too. So let's see. Let's write down what we found. We found our vertical asymptotes at x equals plus or minus root 2. We found our horizontal asymptotes at plus or minus 1. Now we have our critical numbers and stuff, which is good because I'm still not totally sure what this graph is going to look like. Remember, it can cross in the middle. That's not that big a deal. Well, we sort of do know what this graph looks like, right? Because, well, if we plug in a positive infinity, is that going to be less than 1 or more than 1? It's going to be less than 1, right? It's going to approach from the bottom because we still have that little plus 2 technically. It's like we have something like that. So the bottom is going to be bigger by a little bit. So it's going to approach, it's going to go from the bottom. But yeah, and then it's going to have to cross because there's no x-intercepts there for it to cross. So it's going to have to be one of those where we do have some little minimum here. So that's where we're going to have to find the critical number. We're going to have some critical number right around here in between 2 and 4 or something probably. So let's see. For that, we'll have to find the first derivative. So let's do that. We're going to have to use quotient rule. So it's the derivative of the top, which is 1, times the original of the bottom, minus the original of the top, times the derivative of the bottom, which is going to be, what is that? 1/2, 1 over root that, 1 over root x squared plus 2, but then times the derivative of the inside, so times 2x. Oh gosh. At least this is nice. Over the bottom squared, so over just a plain x squared plus 2. Oh gosh. So at least these 2's cancel. And then I'm going to go ahead and try to combine the fractions on the top. So common denominator. So multiply this by root x squared plus 2. So that's just x squared plus 2 minus, I guess just minus x squared over root x squared plus 2. All of that over x squared plus 2. So this is getting pretty messy, but at least these x squareds are canceling out. And then I'm going to keep change flip. So I'm going to end up having, I'll go ahead and write it as, it's x squared plus 2 times root x squared plus 2. So that's x squared plus 2 to the 3/2. So that's not a bad derivative. That's not a bad derivative at all. But then we want to say, when is that equal to 0? And that's never equal to 0. Which is extremely scary. So there's no possible critical values. There should be no max or mins. Which is really weird because we do have those asymptotes there. Which makes you think it's going to have to cross. But the only x-intercepts are at x equals 0, so it can't have any other x-intercepts. So then does it have to approach from the top? But it can't approach from the top because if you plug in 2, what do you get when you plug in 2? You get 2 divided by root 6. You get like a small number. What happens when you plug in like something really, really close to negative root 2? I guess that's hard to say. 2 is kind of the closest you can do there. But we're getting no critical numbers. Did I take the derivative right? Let's confirm that. So it's the square root of x plus 2 minus the x times the derivative of that. The derivative of the square root of x squared plus 2 is 1 over the square root of x squared plus 2 times the 2x So you still have that 1/2, so the 2's are canceling with that, so that's why that's minus x squared over all of that. Minus x squared over the square root of x squared plus 2. So when I common denominator, it's x squared plus 2 minus x squared over all of that. So that checks out. There's none. There's no critical numbers. What do we get when we plug in 1? When we plug in 1, we get 1 over root 3, which is less than 1. I'm just having a hard time thinking about what happens when we plug in something really close to the square root of 2. I guess it goes to, does it go to positive infinity? I guess it would have to, right? But I'm having trouble thinking about how this doesn't have a minimum there. Let me maybe confirm that I took the derivative right. So if I type f of x equals x divided by the square root of x squared plus 2. So that's what the graph looks like. Does it have holes? Oh, we're such bots, or I'm such a bot. There's no vertical asymptotes. This is the square root of negative 2. There's no vertical asymptotes. Oh, I try to do that too fast because it's x squared plus 2 equals 0, so it's x squared equals negative 2, and then you square root both sides, so it's like your vertical asymptotes are at imaginary numbers, which means they don't exist. There are no vertical asymptotes. And there's no problem with the domain. Okay, that makes me feel better about everything. There's no vertical asymptotes. So that totally makes sense then. That's going to come in and be something like that. Is the second derivative, or is the derivative undefined at x equals 0? Does it flatten out at x equals 0? Let's see. If we plug in x equals 0 into the first derivative, it shouldn't flatten out. It should be like 1/2, I guess. Or like, no, 1 over root 2. So it's not going to flatten out. It's just going to come here and be like that. Now, points of inflection. So it's going to have no critical numbers. We found that, and that makes sense now that we see there is no vertical asymptotes, that we messed that up. So now possible points of inflection, we're going to have to take the second derivative. So if I take the derivative of this, let's bring it down here and let's change it to blue. Or change to working in blue at least. So I'm gonna rewrite that 2 x squared plus 2 to the negative 3 halves. Power rule, so negative 3 x squared plus 2 to the negative 5 halves. Right, times the derivative of the inside. So it's 2x over, well, I guess negative 6x over x squared plus 2 to the 5 halves. So if you're finding possible points of inflection, when does this equal 0? At x equals 0. So that's why it does make sense. That's our point of inflection. And you do see that it goes from concaving up there to concaving down there. So that does make sense that that's what our graph is going to look like. Now the slope was not undefined, so it doesn't totally flatten out there or get vertical there, which we can see from here. It looks like it hits a 45 degrees. Which makes sense. That's what we said. Like 1 over root 2 is the slope. Or I guess the slope would be 1 then. But anyway. Yeah. There we go. That makes sense. So I guess that is the main goal of these. Is to just get pictures of the graph. Alright. Should we do another? Or is Rose going to come on? I think Rose is going to come. Alright, let's get back to this after our 2-hour pause. So we're going back, we're analyzing, we're graphing, we're sketching these graphs. So here's the main goal. We're really going to treat this. The main goal is sketching the graph. That's what I'm going to try to do. I'm going to try to sketch the graph, and I'm going to make sure that I get all the important stuff that I need to get to be as accurate as I can with it. So what do we want first? X-intercepts. Let's do y-intercepts first. That's easy enough. It's when x equals 0. You set x equal to 0, you're going to get y equals 0. So we're happy there. X-intercepts, we have to set the entire thing equal to 0. That's a little more work we're going to have to do. So let's write it out. 0 equals 2 times x to the 5/3 minus 5 times x to the 4/3. So what can I do? I can factor out an x to the 4/3. That's what we want. So then I have 0 equals x to the 4/3. And what's left? 2. You're dividing, so you're subtracting those. So there's 1 x to the 3rd, x to the 1/3 left. And then minus 5, because that's all gone. And so all that equals 0. So we're setting both of those equal to 0. So that's how we're getting x equals 0. That's going to be our y-intercept. And then the other one equals to 0. So I'm going to add 5 and divide by 2. So x to the 1/3 equals 5 halves. So then I have to cube both sides to get x by itself. 125 eighths. Oh, lordy. So 2x intercepts, 0, and 125 eighths. I feel like we're trying to do all of this without a calculator. So let me mixed number that so I can actually graph it. So what is that as a mixed number? What's the closest I can get there? So I could get 80, I can get 40, so that's 120. So 120 divided by 8 is 15. Yeah, so this is 15 and 5/8, 15.625. All right, I'm going to write that over here instead. 15.625. Okay. Now, vertical asymptotes. When is this undefined? This function is never undefined. Especially even with the domain, because we're not doing square roots, we're doing cube roots. So the domain is everything. There's no vertical asymptotes. Horizontal asymptotes is also, there's none. Because you plug in x equals infinity, you're going to go to infinity. Yeah, just very clearly you're going to go to infinity. So there's no horizontal asymptotes either. Okay, so now critical numbers and possible points of inflection. We need to use the first derivative for that. Yeah, I'm really not sure what this graph is going to look like at this point. So the first derivative that we can do, that's a power rule. So the first derivative, it's easy enough to just write here. It's going to be 10/3 x to the 2/3 minus 20/3 x to the 1/3. Okay, so for our critical values, we need when does this equal 0 and when is it undefined. So I thought it would be undefined at some point, but that's never going to be undefined. So undefined would end up probably meaning that it's got a vertical tangent line. But this is never going to be undefined. It will equal 0 at a few different places. So if I factor out, I'll go ahead and factor out 10 1/3, 10/3 x to the 1/3. So then I have x to the 1/3 minus 2 equals 0. So this is at x equals 0 and at x equals 8. So those are the critical numbers, 0 and 8. Okay, that's interesting enough. And then for possible points of inflections, we are going to get some verticals for there. We are going to get some undefineds. So let's see. So for the possible points of inflection, we need to take the derivative again. So we take the derivative again, we're going to get 20 over 9 x to the negative 1/3 minus 20 over 9 x to the negative 2/3. And we want to set that equal to 0, so I'm just immediately going to divide by 20 over 9. So the 20 over 9 goes away. And then I'm going to fractionize it, so 1 over the cube root of x minus 1 over the cube root of x squared. We want when is that equal to 0 and when is it undefined. So it's undefined at x equals 0. So there is a possible point of inflection at x equals 0. Interesting, because we also found that as a critical number. So I bet that will be just a point of inflection, not a max or a min. But then let's find a common denominator here. So common denominator, we just need to multiply this by the cube root of x. So then when we set this equal to 0, we're going to have the cube root of x minus 1 equals 0. And so we're going to have x equals 1. So we're going to have another possible point of inflection at x equals 1. And both of those are defined, so those are actual possible points of inflection. So let's see. Let's make each of these blocks 5. So that way we can put our x-intercept just like right here. And then our other one at 0, which is also our y-intercept. We have a critical number at 8. So I kind of just want to plug in 8 into here and see what happens. So I get the cube root of 8, which is 2, to the 5th, which is 32, times 2, which is 64. And the cube root of 8, which is 2, 2 to the 4th, which is 16. 16 times 5, which is 80. So I have minus 80. So that's negative 16. So I have the point 8, negative 16. And I know it turns around there, so that must be that turnaround spot. And then 0 is a possible point of inflection, so I'm guessing that that's not going to be a turnaround spot. But I should probably look at the increasing, decreasing intervals to check and make sure. So let's see, we have 0 and we have 8. So I've already found, it looks like it's decreasing from 0 to 8. So if I plug in 1 into the first derivative, I just have 10/3 minus 2/3, which is negative. So that's definitely decreasing here. And then at 8, after 8, it definitely seems to be increasing, which I don't even need to plug in. I can see that. That makes sense. But the bigger question is if I plug in like -1. -1 is easy enough to do. If I plug in -1, this is going to be 10/3. Because negative is you're going to be squaring it. But then this, the cube root of -1 is still -1, but then it's multiplied by negative 20/3. So this is plus 20/3. So this is 1. So this is positive. So it is increasing over here. So we get then that it's looking like that. Is it really just that simple? Point of inflection at 1, we can kind of see that. It changes from that to that. So it doesn't change at 0, does it? Should I maybe look at those for increasing and decreasing? So let's see. This is like first derivative. Now we're going to look at the second derivative to see the concavity. So I have to plug in like a half, which is super annoying. So if I look at the... Let me look at how this is rewritten. When I rewrote it, it's going to be, you still have the 20 over 9. Oh, but that doesn't even matter when you think of positive or negative. So I'll just leave that on the outside for now. And then I want to be thinking about this fraction. So the bottom is always positive, which is nice. I just need to be looking at the top, actually. The cube root of x minus 1. I just need to see if that's going to be positive or negative. And that's actually super straightforward then. So it's going to be positive. It's going to be concaving up when it's bigger than 1, because that's going to be positive. When it's like a half, you're going to have the cube root of a half, which is definitely less than 1, so it's definitely going to be concaving down there. And then when it's negative, because it's a cube root, the cube root of a negative is still negative, so it's also concaving down there. So that's not a point of inflection at 0. It's just still concaving down. So this is really just looking like a polynomial function. But I think we found everything that we can find by hand. We found that min. Where was that min? Can I just label that min real quick? It was 8, comma, negative 16. And this right here was 15.625, comma 0. Okay, so let's look at the graph. I thought it'd be weirder with the cube roots. I thought we'd have some vertical tangents, because the cube root of x has some vertical tangents. But since we're subtracting them, we're not. We definitely found there were no vertical tangents because it was never undefined when we took the derivative, because it's like this is more than a third. When you took the derivative once, we didn't get any vertical tangents. Oh, see, and that doesn't have a vertical tangent either. Okay. But if I did 1/3, it would have a vertical tangent. And if I did 2/3, it would be undefined for multiple reasons. But with 5/3, we never get the vertical tangent. Okay, that's fair. That makes sense. 5x raised to the 4/3. Ooh, I did 4/2. 4/3. Is that what we found? Yeah. It just makes it weirdly sharp there. That's what's happening. That's not sharp. That's still a curve. Right? Yeah, that's still a curve. Because our derivative was never undefined. We never get a sharp corner. So that's still a curve. And that's exactly what we drew. Yeah. So we make sure we've got this minimum down here we said at 8, negative 16. And then 15.6250. Beautiful. Yeah, we got it right on. Right on. All right. On to the next one. Analyze and sketch the graph of this polynomial. Okay. So standard polynomial stuff. That's not bad. Let's see. I don't have that copied. So let's come back up to here. Copy. Paste. Close. Okay. So I'll go ahead and find the derivatives first. That's easy enough. It's just power rule. So 4x cubed minus 36x squared minus 96x minus 64. Then we do it again, 12x squared minus 72x minus 96. Okay, so definitely going to have some synthetic division ideas going on here. So y-intercept, easy enough. You plug in 0, you get 0. Done. X-intercepts, we got to set the whole thing equal to 0. So if we set the whole thing equal to 0, we're definitely going to factor out an x first. So we're going to have x cubed minus 12x squared plus 48x minus 64. And then we got to use synthetic division. So we could go through the whole deal, find your possible solutions, yada yada. I usually ignore those. I check and see if 1 works by if you add all the coefficients together and they all add up to 0, then you know 1 works, and they don't. So you know that 1 doesn't work. So then I would just try some more numbers. I'm definitely going to try 2 next. And I'm going to guess that that's going to work out for me. So if I do 2, I do 1, 2, negative 10, negative 20, 28. That is 56. So 2 does not work out. Because remember, what you're going for is a remainder of 0. So 2 didn't work out. Really, all that can work is different powers of 2, because it's 64 and that's a power of 2. So let's try 4. Could also try negative 2. But these are big numbers, so something like this, and this is looking definitely good, because 4 times 16 is 64. So there we go. So see, we're working on factoring it. Now we factored out an x minus 4, and we're left with x squared minus 8x plus 16. And right, so now we keep factoring because x squared minus 8x plus 16 is x minus 4 squared. So what we have is x times x minus 4 cubed. Okay. And honestly, from there, so what is our x-intercepts then? 0 and 4, triple root. And just from there, we know a lot, because you think back to Algebra 2, you know what the triple roots do. So we're going to have our x-intercept at 0 and at 4, but that's going to be a triple root. So right away, the whole thing is positive, we saw. So we know that's going to be a point of inflection. That's where it's going to even out. And then we're going to have some minimum down here. That's what we can use our critical numbers to find. Once we find our critical numbers, that's going to be one of them. So one of our critical numbers is going to be 4, because that's where it turns around. The other critical number is going to be wherever that is, something between 0 and 4. So let's see, vertical asymptote's none, it's a polynomial. Horizontal asymptote's none, it's a polynomial. So now we're on to critical numbers. So critical numbers, we got to set the first derivative equal to 0. So that's kind of a grind too, not going to lie. But if I set the first derivative equal to 0, the best thing about it is I can divide everything by 4 right away. So I have x cubed minus 9x squared, 96 divided by 4. 25 divided, or 100 divided by 4 is 25. This is 1 less 4. So that's 24 4s. 64 divided by 4, we just kind of did that as 16. Right, so again, now I have to do another synthetic division to find these critical numbers. So I did say that one of them was going to be 4. I bet we're going to get that 2 of them is equal to 4. We'll get 4 double root here. But if I know that one of them is going to be 4, I should just use that for my synthetic division, because then I should be able to find the other ones. So 1, 4, negative 5, negative 20. Okay, that didn't work. That's surprising. Did I do that divide by 4 properly? Did I do the derivative properly? I did not do the derivative properly, because this should be a plus 96. Got it. If you already commented down below saying I made a mistake, I got you. So that's a plus 24. So that should probably do it then. If I do a 4, 1, 4, negative 5, negative 20, because then I've got a positive 4 and a positive 16. There we go. And honestly, it's working out just how I predicted. We're going to get 4 twice. Because see, now we have x squared minus 5x plus 4. So we factor that, and that's another x minus 4 and an x minus 1. And so that's actually beautiful. We have our critical numbers of 1 and 4. And I'm not going to check the 4 because we already know what that graph does, because it's a triple root. It flattens out there. We get a point of inflection. But now we see where this minimum point is. It's at x equals 1. And then even further, we can find exactly where that point is by finding f of 1. So what is f of 1? That's 1 minus 12 plus 48 minus 64. So you try to put those together. It's not super simple. What's 48 minus 64? Add up, so 6, 10, no, 16. So that's minus 16, so it's negative 12 minus 16 plus 1, so that's negative 28 plus 1, so that's at negative 27. Okay, that's pretty low. So that's at 1, negative 27. But that's where it turns around. We know that now because we calculated it. And then let's see, possible points of inflection. Where are the possible points of inflection? So there it's concaving down. But somewhere here it starts concaving up. So we could find that. We know one point of inflection is definitely 4. So that'll help us finding the other point of inflection. But we definitely find the point of inflection by setting the second derivative equal to 0. So let's go ahead and do that. We'll go 12 x squared minus 72x minus 96 equals 0. And again, we can divide by 12 by everything. So that's not that bad. 72 divided by 12 is 6. 96 divided by 12 is 8, right? Yeah. Equals 0. And so we factor that. And like we already knew, we got the x minus 4 because we had the positive 4. Now we see that our other point of inflection is right here at 2. That's our other point of inflection. So we have possible points of inflection at 4 and 2. We already saw the 4 worked. Now we see the 2 worked. If we wanted, we could get the exact point, but that's not super important. We know it's going to be above negative 27. So let's do it. Also, Mr. I Love Barbecue Chicken, welcome. Let's look at this graph on Desmos and make sure that our graph is looking right. So we're looking for our point of inflection. The biggest thing is we're looking for that minimum at 1, negative 27. That's the biggest thing the graph is going to show us that we need to confirm. So x to the fourth minus 12x cubed plus 48x squared minus 64x. There we go. And we do see that got pretty low, 1, negative 27. We got our point of inflection right around here somewhere, 2, negative 16 it looks like, and that absolutely makes sense visually. You can tell that's about right. And that is definitely the graph that we graphed here. Beautiful, beautiful stuff. All right, on to the next one, and also the last one, I do believe, which is great. So we got a lot of, we got to do the same type of stuff here. So luckily we still have that copied. So let's see. I mean, what are going to be the most important things here? The most important things are going to be things like, there's going to be a lot of important things here. So the x-intercepts. Let's do the y-intercepts first. So the y-intercept, you just make x equal to 0. What do we get when we make x equal to 0? Cosine of 0 is 1. Sine of 0 is 0. So that's 1 over 1 plus 0, so that's 1. So we have a y-intercept of 1, 0, 1. X-intercepts. When does this thing equal 0? When does the cosine of x equal 0? The cosine of x equals 0. Well, we can just go 0 to 2 pi and kind of generalize it, I suppose. So we'll have a period of 2 pi. So 0 to 2 pi will be a decent period to look at. So it's going to be cosine of x equals 0 when at pi over 2 and 3 pi over 2. So those will be x-intercepts. Pi over 2, 3 pi over 2. Vertical asymptotes. When does 1 plus sine of x equal 0? When does sine of x equal negative 1? So that's just once, luckily. That's just at pi. Horizontal asymptotes. If you plug in 0 for x, if you plug in infinity for x, you get a number divided by 1 plus a number. So that's undefined. There is no horizontal asymptote. Okay, now critical numbers. So we got to set the derivative equal to 0. So let's do that. Let's take the first derivative. So we've got to use quotient rule. So we're going to have the derivative of cosine, which is negative sine. Here, I'm going to do it up here. Which is negative sine times the bottom, which is 1 plus sine, minus the original of the top times the derivative of the bottom, which is just cosine, all divided by 1 plus sine squared. And I definitely want to rearrange some of this because I'm going to have negative sine of x. Let's move this up here. So I'm going to have negative sine of x minus sine squared of x minus cosine squared of x. Beautiful. Over, I'm going to multiply this out, over 1 plus 2 sine of x plus sine squared of x. Okay, no, that was not it. That was not it. That wasn't it. This is going to be, is what is this? I factor out the negative. Factor out a negative 1 times sine squared plus cosine squared. So sine squared plus cosine squared is 1. That's why that was so nice. I'm going to factor out a negative again. So I have negative sine of x plus 1 over sine of x plus 1 squared. So one of those is canceling with one of those. So the derivative is negative 1 over sine of x plus 1. That's very interesting. Negative 1 over sine of x plus 1. So this is going to have no critical numbers because that's never going to equal 0 because there's no numerator. But then now what if I take the second derivative? I take the second derivative. It's kind of like a quotient rule thing in a way. is I'm going to have, let's see, I'm going to think about quotient rule. So then minus 1, so plus the derivative of the bottom, which is cosine of x, over the bottom squared. Now, when is that equal 0? There are possible points of inflection whenever this equals 0, which is cosine of x equals 0, which is the same as our x-intercepts at pi over 2 and 3 pi over 2. And the domain, of course, yeah, that's with our vertical asymptotes. So, interesting. So we've got vertical asymptotes at pi, at odd pi's. So pi, 3 pi. I'm going to line it up here. Pi, 3 pi. Is that right? 0 pi, 1 pi, 2 pi, 3 pi. Yeah. Okay. So then we have x-intercepts at pi over 2 and 3 pi over 2. Oh, so there's just every pi. Oh, I'm still doing that, and that's why that's weird. Yeah. Every pi there is one. There are points of inflection, but it has to turn around if it's going to hit both of those points. What? We know we have this. So is my first derivative wrong? I feel like it must be. Let's look at it again. So the derivative of the top, negative sign, times the bottom, minus the original top times the derivative of the bottom. So that's negative sine minus sine squared minus cosine squared. My iPad just died. Oh, my iPad just died. All right, so we're back. iPad's back on. We are redrawing our graph. We're going to do it as, instead of having every block being pi, we're going to have every block being pi over 2. So you see how we have pi over 2 times 3 pi over 2. And we've got still our y-intercept of 1. We've got our vertical asymptote at pi, or at 2 pi over 2. And we're looking back up until 2 pi or 4 pi over 2. So here we should be back up at our x-intercept of 1. So it feels like it's going to be something like that. But that's going to be... That's going to have the first derivative. It's the first derivative is what's throwing me for such a loop. Is that the first derivative is 0. Or is never 0. Is never 0. Let me look at it again. I get the negative sine times 1 plus sine, then minus cosine times cosine. So that's negative sine minus sine squared minus cosine squared. So that's minus 1. So that's negative sine of x minus 1. So that's negative sine of x plus 1 times sine of x plus 1 squared. So that's negative 1 over sine of x plus 1. I'm really having trouble seeing how this is coming out. And we definitely only have that at pi. What about the second derivative? I did get possible points of inflection at pi over 2 and at 3 pi over 2. And so that's the x-intercepts. So what if I plug in pi to the second derivative? It should be the cosine of pi is 0. Oh, right. Well, that's why I did that. Wait, what? The cosine of pi is 0. That's not true. The cosine of pi is negative 1. So you get negative 1. The sine of pi is 0. So you get negative 1. So it's concaving down at pi. What? No, that's not even true. Because the sine of pi is negative 1. So it's got an undefined because it just is undefined at pi. Right. I'm confused how I'm getting no critical numbers. I don't understand how this graph is going to look if there's no critical numbers. I guess maybe I should look at this because then we're going to have the other asymptote here. But we don't have that. And it's not undefined at 0 either. The slope should be negative 1 at 0. I guess they shouldn't be going the same way either. They should be opposite. Is my problem maybe with the x-intercepts is that there's not that many x-intercepts? But no, there's definitely that many x-intercepts. This is when cosine of x equals 0. At pi over 2 and at 3 pi over 2. And at negative pi over 2 as well, right? Yeah, for sure. Just at every other one there's going to be 1. But then the vertical asymptote is only once. So that would imply that you'd have to have times when the first derivative is equal to 0. You have to have like max or mins. But there's not. There's definitely not. I'm about to just graph this and see what happens. Cosine of x divided by 1 plus sine of x. So that is my issue, that I did too many x-intercepts. How is 3 pi over 2 not an x-intercept? The cosine of 3 pi over 2 is 0. The sine of 3 pi over 2... Oh, that... what? So my problem is the vertical asymptote. Sine of pi is 0. The vertical asymptote is not at pi. It's at 3 pi over 2. Oh, that's the problem. The vertical asymptote is not at pi. It's at 3 pi over 2. Oh, what a bot move. What a bot move. Oh my goodness, oh my goodness, oh my goodness. So, the x-intercepts is you do get the 3 pi over 2, but where did I even write that out? I said that sine of x equals negative 1. When does sine of x equal negative 1? At 3 pi over 2. Not pi, at 3 pi over 2. So, that's going to be here then. So then we're only going to have that one x-intercept. So what, at 3 pi over 2, but that also means it's going to be at negative pi. So this is the section of stuff that we're looking for. And then what do we have? Possible points of inflection at pi over 2 and not 3 pi over 2 because that's where it's undefined. So just at pi over 2. So that's where the point of inflection is going to be. So it's going to be cruising through here and it's going to flatten out and then it's going to come through. And it makes sense that that's sort of tangent-ish or cotangent-ish because it's like a cosine over a sine. It's just a little wonked with the plus 1. And so that's what the graph looks like. And that makes sense. Changes concavity at pi over 2. No maxes or mins, like we said. Only thing that was messing up was the vertical asymptotes. Because I was saying there was an x-intercept where there was supposed to be a vertical asymptote. Other than that, it was beautiful. So that's just all these problems. This is definitely the longest one yet. It's been 1 hour and 20 minutes just in recording for 5 graphs, Which is why graphing calculators were such a blessing to the human race, really. Because now you don't have to do any of this. But we were able to get pretty accurate pictures of all these graphs without the graphing calculator. Only one we couldn't was this one. Because, again, I just messed up the vertical asymptote. And, of course, remember this is periodic. So this is just going to, I'm not going to be super specific. But that's just going to go ahead and continue forever like we see here. See, it's very tangentish. Oh, it doesn't flatten out. I didn't mean to say that it flattened out. I should have kind of tested that, honestly. Like, is the first derivative flat at pi over 2? And definitely not, because otherwise you would have got that as a critical number. So, of course, so it doesn't flatten out. That's just where it changes concavity. So it does change concavity. There. But it doesn't flatten out. It just changes concavity. All right, there we go. And there's the graphs. So that was pretty tedious. You don't have to do that most of the time, but you do need to have a good, decent picture of what graphs look like. But I don't know. You don't have to be super specific. You don't have to have a specific idea about what graphs look like, because that's what graphing calculators are for. So, glad that section's over. I'm excited to do the next one.